Welcome back to the Deep Dive. Today, we're putting on our, let's say, cosmic thinking caps. We're diving into the incredible story of the sun. Yeah, this deep dive is all about how that powerhouse up there, 93 million miles away, actually becomes the usable energy that, charges your phone or powers your school. We've got a great set of materials here, really designed to give us the key facts nice and clear. Okay, so let's really unpack this. And this is the big question. Maybe think about it for a sec. How does sunlight, which is just, light and heat, how does that actually turn into the electricity or the warmth we use every single day?
That's the core of it, really, isn't it, that translation? So when we talk solar energy, we mean the radiant energy streaming from the sun that actually hits Earth. It comes as light. It comes as heat. And honestly, this energy is, well, it's the engine for our whole planet. Without that constant flow, all our climate systems, life itself, it would just collapse instantly.
Wow, okay. So how do we actually capture it then?
Right, so basically we give solar energy two main jobs. We can turn it into thermal energy, that's the heat part, like for heating water or buildings. And then there's converting it into electrical energy. And that's where you get, the solar panels we see everywhere. That's the high-tech side.
Okay, this is where it gets really cool for me. Yeah. Before we even talk about catching it, where does all this insane amount of energy actually come from? The sun isn't just some giant light bulb, right?
Not at all. It's a giant, nonstop nuclear fusion furnace. That's the key. Yeah, deep in its core, what's happening is kind of terrifyingly powerful. You have hydrogen atoms getting squeezed together under just immense pressure and heat, and they fuse, forming helium atoms. That tiny change, that fusion, releases a colossal amount of energy. It's basically the most efficient energy factory we know.
And the scale is just hard to grasp. When you say colossal energy, only a tiny, tiny fraction actually makes it all the way to Earth. What are we talking about?
We're talking something like 173,000 terawatts hitting our atmosphere every second. Yeah, and get this. If we could somehow capture all the sunlight hitting the Earth in just one single hour, that amount of energy, it would be enough to power the entire globe for a full year.
1 hour for a whole year. That's incredible. So, all right, if we're literally swimming in this energy, an hour's worth could power everything for a year.
Sure.
That raises a really important question, doesn't it? Why do you think it's so challenging then? Why can't we just capture all this massive energy easily and efficiently? Why haven't we cracked that yet?
Well, it boils down to physics, really, and logistics. First off, the intensity of sunlight, it varies constantly, right? Clouds, night, season. We can't control that. And second, even our best panels, the commercial ones today, they only convert maybe 20 to 22% of the light that hits them into electricity.
22%. That happens to the rest.
It mostly becomes waste heat. Yeah. Capturing that other, almost 80%. That's the huge challenge. That's the multi-trillion-dollar problem scientists are working on.
Right, that makes sense. Okay, so since we clearly can't grab every bit of light, how do we capture some of it? How do we direct it? Let's get into the mechanics, the actual science that makes like a solar calculator work or those big panels on a roof, the photoelectric effect.
Right. So the heart of it is the photovoltaic cell. We call it a PV cell. You stack these into panels, and they're usually made from silicon, highly refined silicon, which, believe it or not, basically starts as sand.
Yeah.
But it's processed into a special material, a semiconductor.
Okay, so imagine it like light billiards. When sunlight, which is made of tiny particles called photons, streams in, it hits the panel, crashes into this silicon stuff.
Exactly. And if those photons have enough energy, they actually knock electrons loose inside the silicon atoms. They free them up so they can move around.
Okay, so electrons are loose, but we need them flowing, right? Like water in a pipe.
Precisely. We don't just want random electrons bumping around. We need a current. We need them to flow in one direction.
And that's where the special silicon comes in. I remember reading it's not just one type.
You got it. A solar cell isn't uniform. It's actually two slightly different layers of silicon stacked together. This forms what we call a PN junction.
PN junction?
Yeah.
Sounds technical.
It is. But the idea is simple. They dope the silicon, meaning they add tiny amounts of other elements. So you get one side, the N type, which has extra electrons ready to move, and the other side, the P type, which has sort of electron vacancies. Little spots where electrons could fit, sometimes called holes.
Okay, extra electrons on one side, spaces on the other.
Right. And this difference creates a built-in electric field right at the junction, where the two layers meet. It's like an invisible slope or a one-way street.
Ah, okay. So when the photon hits and knocks an electron loose.
That built-in field pushes it. It forces the freed electron over to the n side, and the hole it left behind gets pushed to the p side.
So it separates them and forces them to move in an organized way.
Exactly. That directed flow, that movement of electrons in one direction, is the electric current we can use. And then that current goes through wires, it gets collected, and it either powers something right away or gets sent to charge batteries for later. That whole amazing sequence, light, particle hits, electron moves, current flows, that's the photoelectric effect in action. That's how the lights stay on, basically.
That detail really helps understand the how. It's not just magic, it's physics. So, okay, bring you back to the bigger picture. What does all this tech mean for us right now? Why is there such a big push, from governments, from people, for solar energy?
Well, the advantages are becoming really clear, and there are three huge ones everyone points to. First, it's fundamentally renewable.
Meaning it won't run out.
Exactly. As long as the sun keeps doing its fusion thing, which it will for, billions more years we've got fuel, it's not like coal or oil.
Okay, that's big. What else?
Second, and this is maybe the most talked about, it's incredibly clean energy.
Right, no pollution.
Zero air pollution during operation. Zero greenhouse gases. It doesn't need water to run, unlike some power plants. You just eliminate all that toxic stuff that comes from burning fossil fuels when you switch to solar for electricity generation.
Huge environmental benefit. And the third?
The third key point is accessibility. Sunlight, well, it falls pretty much everywhere on Earth, right?
Yeah, some places more than others, but basically everywhere.
Exactly. It's not locked away in specific spots like oil fields or coal seams. This opens up amazing possibilities for, energy independence, especially for remote places or developing countries.
And solar's already kind of everywhere, isn't it? We see the big power plants, obviously, but think smaller, too, like satellites use it, right? Calculators, those flashing road signs.
Absolutely. Satellites, weather balloons, heating water for pools or homes, powering remote sensors, emergency phones on highways, stuff that's off the main grid. So here's something for you listening. Take a look around your own town or neighborhood next time you're out. Can you actually spot where solar energy is being used, maybe on a library roof or a bus stop? Sometimes the panels just blend in, and we forget we're looking at this pretty revolutionary tech right above us.
That's a good challenge. Pay attention to the rooftops.
And thinking bigger, it's interesting to see the global picture, too. Some countries have really pushed solar forward.
Like who?
Well, China, for instance, is huge in manufacturing. They make something like over 80% of the world's solar panels now. And Germany, even though it's not the sunniest place, they were real pioneers with policies. They offered good prices for people feeding solar power back into the grid early on, which made rooftop solar take off there.
Interesting. So policy matters as much as sunshine sometimes.
It really does. And then think locally, like those remote communities we mentioned, maybe up in Canada's Arctic at research stations.
Right. They'd normally rely on diesel fuel.
Exactly. Expensive, polluting diesel fuel shipped over long distances. Solar panels are becoming vital there. They cut down on that dependency, lower costs. Even if the sun isn't super intense all year round, it builds resilience.
Using the sun to be less reliant on shipping fuel.
Yeah.
That's a powerful idea. Okay, so we've seen the amazing potential, the clean aspects, but, nothing's perfect. We have to be realistic. Let's look at the challenges, the downsides. Because understanding those is how we make the tech better, right?
Absolutely. You have to look at the limitations, honestly. And there are three main hurdles people usually talk about right now with solar. First, it's inherently weather and time dependent. That's the big one.
Yeah, no sun, no power.
Right. Sun goes down, power stops, big storm rolls in, production plummets. That intermittency is a major issue for reliability if you want power 2004/7.
Okay, what's number two?
The setup cost, it's still pretty high. The panels themselves, the wiring, the inverters that change the electricity type, installation labor.
So the upfront investment is significant.
Exactly. While the fuel sunlight is free and operating costs are low, that initial price tag can be a barrier for a lot of homes or businesses.
Makes sense. And the third challenge?
Space and storage. Those panels need significant space. You need a decent-sized roof or a field. That raises questions about land use, especially for really large solar farms. And maybe more critically, because the sun isn't always shining, you need storage. Usually big batteries.
Batteries, that's a whole other topic.
It is. You need high-capacity batteries, often using materials like lithium, which have their own supply chain and environmental issues. Plus, batteries are expensive, and they degrade over time. They don't last forever, so that adds another cost down the line.
Okay, let's circle back to that first point, the weather dependency.
Yeah.
That ties right into geography, doesn't it? Like,
Yeah.
how much does your location and the seasons really affect things? If you live near the equator, it's probably pretty steady, right?
Yeah, much more consistent sunlight year-round.
But what if you live somewhere like, say, Seattle or Northern Europe or Canada where you get heavy snow in winter?
Big difference. Yeah, snow and ice can physically cover the panels, blocking light completely. And even on a clear winter day, the sun is lower in the sky, the light is less intense, so you generate less power.
So you almost have to build a bigger system than you need in the summer just to get by in the winter.
That's often the case, yeah. You have to over-engineer it a bit to handle those seasonal dips, which, again, adds to that initial cost.
Right, okay. So challenges are clear. Intermittency, cost, space, storage, location.
But let's flip this. Let's put on our innovation hats. Critical thinking time. Given those known problems, how could technology actually solve them? Think about it. Intermittency, cost, materials for batteries, that 20-ish% efficiency limit. What's the next breakthrough?
Yeah, what's waiting just around the corner? Are we talking totally new materials for panels? Maybe something cheap, flexible, even transparent that could go on windows.
That's definitely being researched.
Yeah.
Things like perovskite solar cells, they're potentially cheaper and maybe even more efficient than silicon eventually. Or different approaches entirely, like concentrated solar power.
Concentrated solar power. How does that work?
That uses mirrors, sometimes huge fields of them, to focus sunlight onto a central tower. It gets incredibly hot, hot enough to boil water, create steam, and do a turbine, just like a traditional power plant.
Ah, so it stores heat.
Exactly.
Wow.
It can store that heat, often in molten salt, and keep generating electricity even after the sun goes down. So that helps with the intermittency problem.
Okay, interesting. So lots of different angles people are working on.
Definitely. The solutions are out there waiting for that next big discovery or engineering leap.
This has been a really fascinating deep dive, just thinking about how simple light hitting silicon, that photoelectric dance, can literally change how we power everything. We covered fusion in the sun, that intricate photoelectric effect, why it's clean, why access matters. It's a lot.
It really ties together physics, engineering, and, well, our future energy needs. And we always like to end with something for you to chew on, right? We talked about the challenges. Now really put on those engineering hats. Think about the near future.
That's right. Here's a challenge question for you. If you were an engineer, maybe working in a lab, and you had, let's say, unlimited resources, money, materials, anything you need, what would you focus on first? Would you try to make solar energy way more efficient, like push that 20% conversion rate up to maybe 50% or even higher? Or would you focus on making it drastically more affordable, cutting the production costs, the installation costs, the battery costs, so that literally every community, rich or poor, could easily access solar power?
Which problem do you think is more important to solve first to really unlock solar's potential? Efficiency or affordability? That's your assignment. Mull that one over. Thank you for joining us on this deep dive into solar power.